Welcome to this exploration of one of the most profound discoveries in cosmology, the expansion of the universe. Throughout this video, we'll uncover why galaxies are moving apart and what this reveals about the nature of space itself. The universe isn't static. Instead, it's dynamic and constantly changing, with galaxies receding from each other in all directions. This fundamental property shapes everything we know about cosmic evolution and the fate of our universe. When astronomers observe the cosmos, they see something remarkable. Distant galaxies are moving away from us in every direction we look. But here's the fascinating part. The farther away a galaxy is, the faster it appears to be receding. This isn't unique to our position in space. Every observer, no matter where they are in the universe, would see the same pattern of expansion. This universal observation leads to a profound insight. It's not that galaxies are flying through space away from each other. Rather, space itself is expanding, carrying galaxies along with it like dots on an inflating balloon. In 1929, astronomer Edwin Hubble formalized this relationship in what's now known as Hubble's law. The mathematical expression is beautifully simple. Velocity equals h naught times distance. Here, v represents the recession velocity of a galaxy, measured in kilometers per second. H naught is the Hubble constant, which has a value of approximately 70 kilometers per second per megaparsec, and d is the distance to the galaxy. This equation tells us that recession velocity is directly proportional to distance. Double the distance to a galaxy, and you double its recession speed. This linear relationship is a cornerstone of modern cosmology. But how do astronomers actually measure this cosmic expansion? The answer lies in a phenomenon called redshift. As space expands, light waves traveling through it get stretched to longer wavelengths. This stretching causes the light to shift toward the red end of the electromagnetic spectrum, hence the name redshift. The greater the redshift we observe, the faster a galaxy is receding, and consequently, the farther away it is. Redshift provides the observational evidence that confirms galaxies are moving apart. It's like a cosmic speedometer, allowing us to measure both the velocity and distance of galaxies across the universe. To understand cosmic expansion, imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move farther apart from each other. Crucially, the dots themselves aren't moving across the balloon's surface. Instead, the surface itself is expanding, carrying the dots with it. This is precisely what happens in our universe. Galaxies aren't traveling through space in the conventional sense. Space itself, the very fabric of the cosmos, is expanding between them. Just as every dot on the balloon sees other dots moving away, every galaxy in the universe observes other galaxies receding, with no special center to the expansion. Cosmologists use something called the scale factor to quantify expansion. The scale factor is a mathematical parameter that describes how distances between objects change over time. By convention, astronomers set the scale factor to 1 at the present day. In the past, when the universe was smaller, the scale factor was less than 1. As we look toward the future, the scale factor continues to increase. What makes the scale factor so powerful is its universality. The same scale factor applies to all distances in the universe simultaneously. Whether we're measuring the space between nearby galaxies or distant galaxy clusters, they all expand according to this single parameter. For decades, astronomers expected gravity to slow down cosmic expansion. But observations in 1998 revealed something shocking. The expansion is actually accelerating. This discovery points to a mysterious component called dark energy. Dark energy is the dominant force in our universe, making up approximately 68% of the universe's total energy density. Its nature remains one of the biggest mysteries in physics, but we know it acts as a kind of anti-gravity, pushing space apart. The discovery of dark energy came from observations of distant supernovae, which appeared dimmer than expected, indicating the universe's expansion rate was increasing rather than decreasing. Let's clear up some common misunderstandings about cosmic expansion. First, galaxies aren't flying through space away from each other like rockets. Instead, space itself expands, carrying galaxies with it. This is a subtle but crucial distinction. Second, not everything in the universe is expanding. Atoms don't expand. The Earth doesn't expand. Even galaxies themselves don't expand. Expansion only occurs between gravitationally unbound structures. Within galaxies, gravity is strong enough to hold stars and planets together, preventing expansion. Similarly, galaxy clusters bound by gravity resist expansion. Only the vast spaces between these bound structures stretch as the universe expands. Let's summarize what we've learned about the expansion of the universe. First, galaxies recede from each other because space itself is expanding, not because they're moving through space. Second, Hubble's law provides a quantitative relationship. The farther away a galaxy is, the faster it recedes. Third, redshift gives us observable evidence of this expansion, allowing astronomers to measure both distance and velocity. Finally, dark energy, the most abundant component of the universe, is accelerating this expansion. As time marches forward, the universe continues to grow, with galaxies drifting ever farther apart. This ongoing expansion connects us to the universe's origin in the Big Bang and hints at its ultimate fate in the distant future.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.